Good morning, participants. Good morning to all the participants. Welcome to the today's session. Today, the speaker is Dr. Srilendra Kumar Dwivedi sir from National Institute of Technology, Bhopal.
A very good morning, dear participants. I hope you are all doing well. Welcome you all to the second day's program on trends and challenges in development of electric vehicles and hybrid electric vehicles, Series 1. This morning we have Dr. Shailendra Kumar Dwivedi from National Institute of Technology, Bhopal, who will be speaking to us on the topic integration of multi-spot EV-based charging infrastructure. Before I give this time to sir, I would like to invite our convener for this event, Dr. Sridhar sir, to introduce the speaker. Over to you, sir.
Good morning to Dr. Srilendra Kumar sir. Welcome, sir. For
Hello, good
today's
morning.
session.
Good morning, sir. How are you?
Fine, sir. Welcome, sir.
Yeah. Thank you. Thank you so much.
Participants are ready, sir. Before that one, I want to introduce you to the participants.
Yeah, sure.
Dr. Srilendra Kumar Dwivedi sir is with Maulana Azad National Institute of Technology, Bhopal, Madhya Pradesh. Then to give complete introduction, it will take a long time. I want to concise his credits. Dr. Shailendra sir completed BTech in Electrical and Electronics Engineering from Bharat Institute of Technology, Meerut. MTech in Electrical Engineering with a specialization in Power Electronics, Electrical Machines and Drives from Indian Institute of Technology, IIT Delhi. During the coursework of PhD, he received honor from the Minister of Electronics and Information Technology Assistantship from Government of India. That is his credit during his PhD program. Then after PhD, he did postdoctoral research work from Khalifa University from Abu Dhabi. Then he joined SV National Institute of Technology, Surat. Then he shifted to Maulana Azad National Institute of Technology, Bhopal. Then he published papers in Science Citation Index journals. Nearly 40 he published. And he has 4 patent grants. And he presented papers in international conferences, nearly 65. He has professional affiliations also. He is a professional member of IEEE, that is Institute of Electrical and Electronics Engineers, and his reviewer of various journals at international level, such as IEEE and IET. Then he has good international exposure also. He visited Imperial College London, England, for collaborative work related to reliable and efficient systems for community energy solution project. He visited University of Churchland, Scotland, for collaborative work on optimal control for grid integrated solar PV energy conversion system. He visited University of Nottingham, United Kingdom, for collaborative work related to joint UK-Indian clean energy project. And he presented research paper in annual conference of IEEE held at Beijing, China. He has good exposure related to this concept of electric vehicles and related troubleshooting problems and research going on at present. Now, sir enlightened us related to the concept of integration of multi-spot EV-based charging infrastructure. Welcome, sir. Dr. Divedi, sir.
Yeah, thank you, Dr. Sridhar, for such a nice introduction and explaining what I have done in last 7 to 8 years. Not taking much time, I'm going to share my slides and then we'll be having next 1.5 hour what we are going to have in this particular session. So is this my PPT is visible to all?
Yes, sir.
Someone confirm?
PPT is visible, sir. Visible.
Yeah, and it is also moving. Is it moving? Can you?
Yes, sir. Yes, sir.
Yeah.
Sir,
Okay.
PPT is visible and the slides also nice, sir.
Okay.
Please adjust your camera, sir, because please down the camera.
Okay. 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 So
PPT slides are nice, sir. Okay, sir.
yeah.
Now it is okay, sir.
Okay. I think now it is okay.
Yes, sir. Yes, sir.
Yeah, so thank you so much again.
Sir.
I would like to thank for inviting me for this particular talk and to give talk in this particular FDP. So here, as the focus of this particular FDP is for electric vehicles and hybrid electric vehicle kind of thing. So I have chosen a topic in this particular because this is the new challenge for electric vehicles. When we are talking about many pupils, many industry, they are talking about the electric vehicles. But if we talk about any new technology, then we have certain challenges. Okay, so here today, as I'm electrical people, and this FDP is, I think, organized by mechanical engineering, and also electrical people are also involved. So electric vehicle can be categorized into three parts, basic three part. One is as mechanical people give the design of overall electric vehicles, even though not for electric vehicles, for any kind of vehicles. If you talk about automobile based cars or automobile based bikes, so design is also important. How much weight you are going to put along with this electric vehicle, so accordingly you can get the mileage will also be affected by the weight of electric vehicles. So overall design of these vehicles are I mean, designs, we have various designs, various two-wheeler, three-wheeler, as well as four-wheeler designs. So design is directly affecting the consumption of fuels, how much fuels can be consumed by the particular vehicle. So here design aspect, one of the area where we can work, and mechanical people continuously they are working hard. The other aspect in terms of electric vehicles, if we talk about, is motor technology, motor or drive technology, we can say. So in case of electric vehicles, and these electric peoples are continuously working on these special machines. Special machines means PMSM drive, permanent magnet synchronous motor drives. Synchronous reluctance based machines where there is no magnet. So they are having their advantages and disadvantages. If you talk about induction motor, so stator as well as rotor side, we have to put some winding. So, I mean, losses and efficiency of that particular machine is low as compared to special machines. If we compare the PMSM, permanent magnet synchronous machine, with the induction machine, so this rotor side, we are having a rare earth magnet, which can reduce the rotor losses. Ultimately, because if we talk about any kind of machines, the majority of losses are coming from the rotor only, because we are going to load the rotor, mechanical load we are putting on the rotor. So I square R losses are playing major role in the machines, and efficiency of that machines are, I mean, this efficiency is kept down. So if you want to improve the efficiency, we have to reduce the rotor losses. Okay, so this way this PMSM is more effective as compared to induction machines. The other machines, so PMSM is also having disadvantage, as we are having this permanent magnet on the rotor side. So sometimes leakage current as well as this saturation of magnet playing a major role in case of PMSM. So people came across the synchronous reluctance machine. Synchronous reluctance machine means we are not having any kind of winding over rotor, as well as we don't have any kind of magnet on the rotor. So how the torque is going to be generated? Torque is generating through reluctance only. Reluctance is playing major role in these machines, and these torques and MMF, all those things are generated through the control as well as from the reluctance. So these machines are quite important in case of developing these electric vehicles. So second aspect is of the electric vehicles is motor drive technology. How machines we can make these very effective for electric vehicles. We have to reduce the size. You keep in mind, we have to reduce the size so that the battery power can be, means raise extension can be done. We cannot say like my car is running for 300 kilometers. When I'm putting another motors, the range of this electric vehicle is reduced to 250 kilometers. So we have to go on, keep on working, like if you are going to use special machines, the size and weight of the machines will be lesser, as well as efficiency of the machine will be lesser, so that we can draw less power from the battery, so that this same battery can be utilized. If your my vehicle is having 250-kilometer range, it can be extended up to 20-30 more, 20-30 kilometers more. So this way we can have these motor drive technologies. So all these, but the when we are working on another aspect, the other factor may also deteriorate. So in case of synchronous reluctance machine, the power factor is very poor. So what would be the solution? Because once you are putting these machines along with the battery, or when we are going to integrate these battery with the electric vehicles and this synchronous reluctance motor drive. So once the power factor is poor, we are drawing reactive power. So what would be the solution? Solution is we can put some magnets on the rotor side. Okay, we are having some structures, and in these structures we can put the small magnet to improve the power factor. So people are calling it PM assisted synchronous reluctance motor drive. Okay, permanent magnet assisted synchronous reluctance motor drive. So my power factor is also improved. A small magnet, that is not the means rotor is not made up of magnet only. A small magnet we have put in rotor bars. Okay, there is slots in the rotor. In these slots, we can put the small magnet material so that we can improve the power factor of the supply. So that the of the machines, we can say, so that it should not draw any kind of reactive power, and the efficiency is improved. The size of the machine is quite low as compared to PMSM as well as induction machines. So I mean, this way we can improve the motor drive technology. Second aspect. Now, third and very important aspect, battery management system, or how you will provide the power to the battery. Because once it is fully discharged, you need to charge this battery. You require some kind of energy so that we can charge it, and again we can run our vehicles. Otherwise, what will happen? Once, suppose we are moving in some urban area, in rural areas, and my vehicle range is 250 kilometer, and we don't have any kind of charging station or facility of charging in within this 250 kilometers. So what we have to do? We cannot continue moving, or we can get interrupted. My vehicle cannot run further because we are having a 250 kilometer range once it is charge 80 or in 90% SOCs. So these charging infrastructure are playing major role in developing of EVs. Everywhere you will find out the government is focusing on these developing of charging infrastructure, because same concept you can apply as automobiles. Everywhere you will find out the petrol pumps, even though in urban areas as well as in rural areas. Within 10 kilometers, in urban areas 2 to 3 kilometers range, you will find out the petrol pumps. So we want the charging infrastructure similar to the hello. Yeah, I'm still on first slide.
Thank you, sir.
Okay. Yeah. So in this case, the third and important thing is charging infrastructure. So today, the motive of today's lecture is how this charging infrastructure will affect the grid, number one, and how we can integrate these charging batteries or multiple EVs which are having multiple voltages. I can charge multiple voltage based EVs. What do you mean by multiple EVs based, multiple voltage based EVs? I'm having a Mahindra Vitario car, which the battery voltage is 72 volt. I'm having a Nexon EV, which is having more than 300 volt battery voltage. I'm having Tesla car, which is having a battery voltage of 600 volt, and 100 ampere hour batteries, 150 ampere hour batteries, 200 ampere hour battery. So by developing same infrastructure, I can charge multiple voltage based cars, as well as I can also charge two-wheeler, three-wheeler based vehicles. So this charging infrastructure is means the motive of developing this charging infrastructure so that we can integrate multiple vehicles or multi-spot vehicles, multi-voltage based vehicles. However, if you see the other side, if you are putting these multi-spot EV, large number of EVs on the grid, the supply will be, sometimes you will draw reactive power, sometimes the power factor of this grid will be poor, as well as we will increase the burden on the grid. As peak demand during the peak hours, like my loads, home loads, other loads are more, and extra you are putting EV on the grid. So what will happen? Further you are deteriorating the grid, or the burden on the grid will be large, and sometimes or it may be possible the grid may collapse. So what would be the solution? We have to also integrate renewable energy to support this grid. So here we have selected one renewable energy sources that is freely available, and it is solar energy system. So solar PV array is also integrated along with it, so that we can provide the power to the vehicles, as well as we can reduce the burden on the utility grid. Okay, so some of the topology I'll show, but first we will brief what are the charges, what are the charging stations, and what would be the motivation and objective for developing these kind of charging station, which I told you. So if you see the first point, the charging station is supported with the synchronization and seamless mode switching control. What do you mean by seamless mode? So the charging station which has been developed till now, they don't have the facility. Either they are standalone, I mean they don't have any kind of interaction with the grid, means we have put the solar, and solar is used to supply the power to charge these vehicles, or we are having these grid connected vehicles, by which grid is available, and from the grid we can charge our vehicle. But in this charging infrastructure, seamless transition is also there. From standalone to grid connected to standalone. Sometimes grid is not there, so solar is utilized. If solar is down, then we can put these vehicles to the grid, so that these vehicles can be charged from the grid. However, if you see the conventional charging station from the protection region, they are mandatory to shut down automatically at the loss of grid. When there is no grid, because your conversion is always required. Sometimes you will find out the onboard and offboard chargers, onboard chargers and offboard chargers. So in case of onboard charger is along with the vehicles, and these vehicles, they are having some converters, AC to DC as well as DC converters. So in that case, these are the plug-in. There is plug, and we can directly plug on plug on the supply, and we can charge our vehicle. But the weight of these vehicles will be higher, as they are carrying continuously these two converters. Okay, so they are consuming more power, and the battery may deteriorate within 3 years. So that is the one of the aspect. So we have to convert this DC power into AC. Solar, we have to convert this. Solar is giving DC, so we have to convert this DC into AC to charge on board based vehicles. They are slow chargers. Okay, they are slow chargers. So this DC to AC converter is required in that case. Okay, and we have to control this voltage source converter. So voltage source converter is nothing but it is going to convert DC power into AC. So we can provide the power to the onboard vehicle. So if this converter is controlled in grid connected mode or in current control mode, and we are switching from grid connected to standalone. So conventional converter, when grid lost, we cannot have control over voltage source converter. So what will happen? We have to shut down our charging station, and we cannot charge the vehicles. That is the main disadvantage of this particular conventional charging station. How this particular problem has been addressed in this talk, or in this particular topology, which we will show. So in PV based charging station, extracted active power is shared between the load and the utility. Moreover, this charging station can be operated under outage of PV source and utility grid in vehicle to grid mode. So what will happen if we are operating this particular converter or this particular technology in vehicle to home mode? How we can provide or how we can operate this particular charging station in vehicle to home mode? Means some kind of emergency loads are also there. So these charging station, when the vehicle loads are less in this particular charging station, we can also utilize power to supply homes or nearby hospitals, data centers, because they cannot afford the loss of utility grid. You can think the hospital, can it suppose some doctor is doing some surgery or some operations, he cannot afford the loss of electricity. If electricity gone, he cannot do the operation, or sometimes it may stop these functionality of hospitals. So we require continuous power, and nowadays urban cities, they are stopping using of these diesel generators, because this diesel generator emitted very harmful gases. So Ministry of Renewable Energy as well as these government, they are going to avoid diesel generator, and they are not going to encourage if you are putting this diesel generator along with your systems. So this way, if we are operating this vehicle to home mode, which may increase the utilization factor of charging station. Same converter need not to do anything. Same voltage source converter will be controlled in such a way so that if you are having any kind of battery bank at the charging station, this battery bank can be discharged to supply power to the emergency loads, we can say. This charging station is also enabled with the vehicle to grid. If vehicle is there, suppose somebody is working uh, in some industry, IT industries like in Hyderabad or in other cities, other urban cities, Mumbai, Hyderabad or some Bangalore. People came to office at 10 o'clock, they park their vehicles and they do work till 4 or 5 p.m. and then again they leave for home. So during this time, if one of the vehicle suppose is fully charged at 10 a.m., somebody came from home and they have charged their vehicle yesterday. So the power of that vehicle we can utilize to support the grid, because most of the load when we are going to when these offices all those are functioning at 10 o'clock or 11 o'clock, the load on the utility grid will be more. So in that time, all the vehicle can be connected to grid so that they can support the grid. They can support the grid and the load demand can be fulfilled. Load demand can be fulfilled. So this way we can have the exchange of active power. However, the other side, we can also have the reactive power exchange. So suppose I'm having a voltage source converter. So this voltage source converter is controlled in such a way so that it can also supply the reactive power whenever it is demanded by the grid or it is required by the load. So we can have the unity power factor operation from the grid side. The other side, vehicle to home power transfer, so supporting the local loads in islanded mode. So there are two aspects which I told you. One is we are going to control this charging station in current control mode. The other aspect, we are going to control this charging station in voltage control mode. So that we can have the continuous supply to the vehicles. I would not say, like, I cannot say like my grid is gone, so I cannot supply power to the vehicles. My renewable energy available, so at that time, at that moment, I can supply power to the vehicles. If it's similar kind of thing, like you are going a petrol pump and if petrol pump says I don't have fuels or I don't have diesel and petrols, they are, I mean, restoring immediately. They are giving these so we have to also store this power, so we are putting one extra battery bank there. If both the candidate like renewables as well as this grid are not there, at that moment battery bank is there which can be utilized to charge the emergency vehicles or vehicle which are at the station. So this kind of facility we are providing in this particular charging station. So priority is we have to provide the power to the vehicles. So integration of these kind of vehicles is in demand due to higher fuel prices and cheaper PV modules. Continuously, the cost of these PV modules are I mean, in coming time it will, because as the manufacturing is going to be increased. So, and these people are buying these PV modules, so the cost is becoming down and down. What are the other benefit of proposed charging station? Reduction in the distribution losses, as we are compensating these losses, as well as we are providing uh, reactive power compensation from the converter. So distribution losses are reduced. Bidirectional power flow capability. We can, if my vehicle is not there, at the charging station, battery is fully charged, and I mean, we don't have much load on the grid. So this uh, solar can be utilized, the solar power, extra solar power can be utilized to fed to the grid, so that we can earn the money. We are indirectly we are selling the money to the grid users. However, the other aspect, we can also import the power when we require. Suppose solar is down and battery is SOC is not maintained. So battery state of charge is also limited from 20 to 80%. Certain below 20%, we have to protect the battery. We must not discharge the battery below 20%, and above 80% we should not charge the battery. Okay, so between 20 to 80% we have to operate this battery bank. So if it is hitting the lower limit of SOC, we cannot discharge it. So we need to charge it. So this time battery is hitting lower limit, solar is not available, and grid is there. So we can import power from the grid and we can charge the vehicle. We can charge our battery bank also, which is developed, which is at the charging station. Indirect cost reduction. The another aspect in control side, we have this PV feed forward loop. Okay, we have incorporated PV feed forward loop. So I'll show you how this PV feed forward loop is playing major role when suddenly there is increase in the EV loads. So there is, I mean, oscillations in the grid current. So these oscillations can be reduced by putting this PV feed forward in current loop, which indirectly or directly will improve the dynamic response of the system. The charger is also controlled to operate as an active power filter. As I told you, it will mitigate the load harmonics, mitigates the harmonics when the heavy EV loads you have put, because on board charger, they are having certain converters, certain power electronics devices are involved. So they draw certain harmonics. We have to take care of these harmonics also. So here this converter, the main body of this particular system is utilized to mitigate the harmonics, and grid current TSD, total harmonic distortion, is maintained within the 5%. That is, IEEE 519 standard says it should be less than 5%. Now, from this particular slides, we will see the scenario till date, or not till date, I would say. This is the data which we have collected in before 6 months, I think, before 6 to between 1 year. So I think in December 2021, I have collected this data. So what I found, like the government of India, they have taken the step to improve the charging facilities of electric vehicles. So here I have mentioned various part of India, like various states of India's, and in first, so they have launched two schemes, FAME 1 and FAME 2, faster adoption and manufacturing of electric vehicles. Okay, FAME 1 and FAME 2. So in FAME 1, what they did, the FAME 1 was, they have launched in 2015, I think. From 2015 to 17, they have, I mean, they have seen like how many charging infrastructure can be developed. So in first phase, they have developed 314 charging stations, and they have installed in various part of country. Like in Jammu and Kashmir, they got they didn't get any kind of charging station in first phase. I mean first phase. Okay, Chandigarh got, red one is showing like how many charging stations are installed in phase 1. So Chandigarh, Delhi, Rajasthan, Karnataka also got 37 charging station. Himachal Pradesh, Uttar Pradesh, Jharkhand, Telangana also got 30 charging station in FAME 1 from 2015 to 17. Now, as the technologies, improved from the vehicle side, so people are now people had focused on these electric vehicles. So again, the charging facility has to be developed. So the government of India has taken another steps, like they have developed the second scheme, and they have launched the second scheme, like FAME 2 scheme, phase 2 schemes, and they have installed 2867 charging station. And earlier FAME 1 was for 2 years. Now they have launched for 3 years. And how much they have invested? 10 crores rupees they have invested to develop the charging station, because they have understood what is the importance of charging station. If we want to adopt the electric vehicles, we must have this kind of facility. Otherwise, slow charging, these 230 volt and 15 ampere socket cannot charge your vehicle within half an hour, within 15 minutes. So these charging facilities, these fast charging station are main requirement or main component of the to adopt these electric vehicles. Okay, these fast charging station. And you won't believe, right now private industries are also coming forward. They are also developing their own charging station. Like I have heard, Tata has developed in somewhere in Karnataka, I think they have developed their 50 kilowatt charging station. Somewhere in Chandigarh, in between Delhi and Chandigarh, this Tata or some other company, they have developed this solar-based charging station. Only solar. They have not integrated any kind of grid, but they have developed. They have installed 100 kilowatt solar, and they have made these charging points. They have put some DC-DC converter as well as DC to AC converter, so that both the vehicles can be charged. I mean, onboard and off-board vehicles can be charged through these facilities. So these are the development I wanted to show. So in second scheme, almost every states, not every state, but most of the states, they got the charging station. Even though in hilly areas, Uttarakhand also got these 10 charging station. Because in Himachal and Uttarakhand, we are having hydro power plants, various hydro power plants, and they have also installed the solar power plant. But hydro power plants are playing a major and crucial role for developing the charging station, because sometimes we are not able to accessibility of the grid is not there. So they have utilized these hydropower plants, and they have developed these charging station, 10 charging station in Himachal Pradesh and second phase or in FAME 2, and Uttarakhand also got 10 charging station. And other states, Kerala, Karnataka, Andhra Pradesh got, I think, second highest numbers charging station, 266 charging station they got. However, Gujarat got this 278. Largest states who got these 278 charging station. So this was the development before, say, 1 year, I would say. Not because we have to we have seen or we have collected data in December. It may be this scheme they have developed from 2019 to 22. So all the charging station nowadays, it may go beyond these 2867. So 5,000, 6,000 charging station may be there to develop the charging station. So this was the main. Why my slides are not moving?
Sir, cursor is moving, sir.
Yeah.
Cursor is
Yeah,
moving
now
on the
it-
map.
Okay, so here we are having introduction. As I told you, the status of charging stations, I mean FAME 1 and FAME 2 in India, and how many charging station we have. The government of India, they have taken the initiatives, as well as now private industries, EV industries also taking these initiative to help to develop these charging station. Now, if we see the chargers, type of chargers which are available in this scenario, so if we see the chargers are categorized in two parts, that is home charging. So home charging, as I told you, a single phase socket, I can draw, or we can draw maximum 15 ampere current from that socket. So hardly we are getting, suppose the vehicle battery is quite large, so it will take time to charge it. So you might have had like three-wheeler or two-wheeler, they put their vehicle on the grid for 6 to 10 hours or to these sockets, and they run the rickshaw on daytime, and nighttime they use to charge. So this is the home based and slow charging. Now, if you see the public charging can be categorized into two parts, AC chargers and DC fast chargers. We are also having in AC chargers, we are having a normal chargers like onboard chargers, as I told you. In case of three-wheeler, this onboard charger along with the rickshaw, we can put this charger directly on the single phase socket. However, AC chargers are also fast charger, fast charger which are installed at the charging station, and these chargers are rated from 7.7 kilowatt to 22 kilowatt. So if any suppose I'm having a Tesla car and it is rated, the battery of this Tesla car is rated for 22 kilowatt hour. So how much time it will take to charge from a single phase socket, 230 volt 15 ampere socket? Almost it will take 8 to 10 hours to charge these vehicles, which is not adopted because you are running from suppose 250 300 kilometer, and my vehicle range is 250 kilometer only. So after 250 kilo, I have to charge, or I have to come back from that place to my native place, or somewhere from here to where I'm moving. So what we have to do, we should have the charging facility at the end of my journey, and I can again charge my vehicle within 15 to 20 minutes. It is not, I cannot stay like if I have to return on the same day. So I cannot say like I will give you 5 to 6 hours to charge my vehicle. I will not allow, because I have to return back to my original place. So what we have to do, we have to develop these AC fast as well as DC fast chargers. So here DC fast chargers are categorized from 10 to 50 kilowatts, and they have categorized into two parts, like level 1 DC chargers and level 2. So in level 1 DC charger, the voltage is quite low. You can see here, in case of level 1, the vehicle voltage or the battery voltage is 48 and 72 volt, and 200 ampere hour battery is there. However, in case of level 2, the voltage is quite high. We can have, because in Tesla cars or in some other cars, they are operating more than 600 volts, so that the battery current can be reduced. So output voltage up to 1000 volt with power output of 30 kilowatt to 150 kilowatt. So this is the categorization of charger. What are the charger and what are the public and fast and slow charger, and according to their ratings. Okay, so public charging infrastructure installed in India. If we see the Ministry of Renewable Energy website, we'll find out this particular how many chargers we have developed, fast and slow chargers. And in this combined charging system, minimum 50 kilowatt, the voltage range is 200 to 750. So we can charge the vehicle from the range, which range from 200 to 750. One connector gun, and we can charge four-wheeler. However, other type charges are there. They are rated from 200 to 50, 500 or higher voltage. One connector gun is there, and it is also for four-wheeler. However, if you see the type 2 AC charger, minimum 22 kilowatt, the range of voltage is 380 to 415 volt. One connector gun can be used to charge all three types of vehicle. We can charge four-wheeler, three-wheeler as well as two-wheeler. Other side, we are having slow moderate charges like Bharat DC 001, Bharat DC which is rated to 15 kilowatt, and other Bharat AC 001 which is rated to 10 kilowatt. But for Bharat DC 001, we are having two ranges of voltages, 48, 72 volt. However, for Bharat AC 001, we are having 230 volt AC. So here again one connector gun can be used for 48 and 72 volt. However, for 48 volt, because the battery many times you'll find out the drives as well as these battery vehicle which is rated at 48 volts. So four-wheeler, three-wheeler and two-wheeler can be charged from the same connector gun. However, for Bharat AC also we can charge from this three-wheeler rickshaw, two-wheeler bike as well as four-wheeler car from these AC chargers. So as I explained, home charging, maximum 2.5 kilowatt power we can take in 1 hour. So this is the slow charges. However, public charging is, I mean, according to Bharat EV standard, and that recommends like electric power needs to be built and payment needs to be collected. So they have put some machines, cash collections machines as well as card collections machines so that we can pay the bill during when we are going to charge these vehicles. So this we are having also some standard which supply the AC current to vehicles on board charger, which in turn convert AC into DC along the battery to be charged. Normal AC charger they are rated from 2.5 kilowatt to 3 kilowatt. And as I told you, if you want to charge a vehicle which is rated at 12 kilowatt hour, it will take 5 to 6 hours. A battery of a vehicle is rated to 12 kilowatt and we want to put a single charge. Means I'm telling you why the charging infrastructure is required. Everybody is saying like at my home I'm having electricity, then I can charge my vehicle. No, because it will take more time. So we want to reduce the time, and also battery should accept the higher amount of current. Okay, battery should accept. I cannot say like the battery rated is 7 ampere hour and I can put 14 ampere hour on the battery. That is not acceptable. Okay, so battery rating is must be quite high so that it can accept higher current. So if you are putting 12 kilowatt hour battery to charge my vehicle, it will take 5 to 6 hours from the single phase socket. Okay. So this way we are having, that's why people have launched this or developed this fast AC charging so that Nissan Leaf or Tesla car can be charged, because these cars are rated from 7.7 kilowatt to 22 kilowatt. And DC fast charging, they have categorized as we have seen in figure, level 1 and level 2. And these, as per Bharat EV specs, these will be called level 1 DC charger if the voltage range is from 48 to 72. And they are rated 10 kilowatt, 15 kilowatt, maximum of 200 ampere hour battery we have to connect. And other side, we are having 3150 kilowatt, which is known as DC, level 2 DC fast charger. Now I'll show you how we can have the technology. This was all about how many chargers are there, how we can go for the, how many charging station we have installed in India. Now, actual research, our research is going to be start from here. How we can connect our vehicle battery with the grid, with the renewables, and how we can improve, address these when the heavy current is drawn, and all the functionalities like vehicle to grid, vehicle to load, smart chargings, as well as vehicle to vehicle, vehicle to home, all these functionality, how we can take from the system. So if we classify solar based PV charging station, which is also integrated with the grid, it is categorized into two parts, single phase and three phase. Single phase is again slow charger. So they have categorized in single stage, two stage also. So here we can put EV battery without control. We can see from our eyes like SOC of the battery is now 20%. So we have to disconnect the battery, or SOC of the battery is 80%. So we have to, we can now discharge the battery, we cannot charge it. However, if you put the control over it, EV battery can be with the bidirectional converter we can put. So this converter can be controlled and we can have the charging and discharge control from the DSP control or from our controller to control this EV battery. However, other side we are having two stage. So single stage, two stage means this renewable is connected with the converters or without converters. MPPT can be maximum power point tracking you have heard earlier. So this solar is required some kind of MPPT. So here in single stage, this MPPT has been done with the bidirectional converter only. We are not putting any kind of converter along with the PV array. People are putting boost converter. Now, in case of two stage, we can put the boost converter, but in single stage, this MPPT, all the power extraction from the PV array has been done from the bidirectional converter. So there are two functions which has been achieved from this bidirectional converter. One is extracting the maximum power from the PV array, operating as an MPPT unit, as well as it will also control the battery charging and discharging current. As we have certain limits, 20 to 80%. So below 20%, it will disconnect the battery or it will not provide any power from the battery. Or when 80% it is hitting, so it will not charge the battery. Okay. In similar fashion, these three-phase charging stations are also categorized: three-phase, three-wire charging station, as well as three-phase, four-wire charging station, because sometimes we require to compensate this unbalancing also. Okay, so we cannot say like from the three-phase we can address this unbalanced system, like neutral current is drawing more current when the unbalancing is happening. So in case of three-phase, four-wire charging station, we have to use extra leg for the voltage source converter, and then we need to charge our vehicle so that this neutral currents keeps on tracking, and this fourth leg is utilized to mitigate this grid neutral current. Okay, this way again, EV battery without control, this three phase is also categorized into two part, how we can go for the EV battery with control, without control, and all those things. So this is the first topology which we have developed in the laboratory, I would say. So here we are having solar PV array. This is the two-stage topology. So here PV array is there. Number of series and parallel modules will decide the PV array rating. And then we are having this boost converter. Other side, on the same DC bus, we have connected one vehicle. Here you can see that we have connected one vehicle, and this is the bidirectional converter. So we are having inductance, and then we are having these two switches. So this converter will decide, or the charging and discharging, or this DC bus will decide, like we need to charge the vehicle or we need to discharge the vehicle when we have parked the vehicle, and then we have this kind of operation, we want to charge and discharge the vehicle. This boost converter is responsible to do the MPPT. However, this bidirectional converter will maintain the DC voltage across this capacitor, as well as maintain the current which is bidirectional in nature. When we want to charge it, it will flow from CDC to it will flow from this way. Okay, so this switch will be turned on. However, if we require some kind of support at this DC bus, suppose the grid is not there, the PV component is also not there, and we have connected some hospitals, and this EV is available to discharge. So what we will do, this converter will operate in such a way so that this EV battery can be discharged in this fashion, and we can get the power here. So this unit, this voltage source converter will be controlled in voltage control mode because grid is not there. When grid is there, this converter will be controlled in current control mode. So there are two aspects like current control and voltage, because control, power electronics control is very important. Electrical control is very important for these systems. So in grid connected mode, the charger allow EV owner to sell the EV energy to the grid for revenue generation in vehicle to grid mode. Vehicle to. So suppose grid is there, load is not there. In that case, we can discharge this EV through this VSC and we can send the power to the grid. So that we can have this particular revenue generation when the EV need not to charge. And certainly like PV array is more and SOC is not maintained, so we can charge this vehicle, as well as if extra power is available from the PV array, we can send directly to the grid from this voltage source converter, so that we can sell the power to the grid and we can generate the revenue and we can improve the factor of this charging station. During outage of grid and PV array generation, the charger utilized to EV to supply the household load. As I told you, during a standalone mode, grid is not there, PV array is not there, then we can utilize same concept or same battery here to supply non-linear loads. So these non-linear loads, because nowadays most of the loads are connected at the point of common coupling, are non-linear in nature, or I would say power electronics based loads. Here you can also connect some onboard charger also. Onboard charger, what it will have? It will have this AC to DC conversion unit, AC to DC, and this may have, after capacitor, it may have some DC-DC converter also, some DC-DC converter. So these DC-DC and AC-DC, they will generate certain harmonics and they will pollute this grid, So some kind of facility we require so that we can mitigate these pollutions. Pollution is nothing but, in electrical engineering, pollution is harmonics. So we have to integral multiple of fundamental frequency. So grid always required which kind of waveform? This sinusoidal waveform. This sinusoidal waveform. And this current and voltage should be sinusoidal and in phase. Whenever power is being fed to the grid, then it will be in opposite phase, current will be in opposite phase. However, if we are drawing power from the grid, then they will be in phase. So unity power factor can be maintained during injection of power to the grid as well as drawing power from the grid when EV battery we are going to charge from the grid. So this way we are having whole operation, and you won't believe all the function, charging, discharging, requirement, power requirement, load demand requirement, and this renewable energy is outage or generation is there from the renewable, all will be done by the control only. We need not to switch on, switch off, and we need not to take care of all the things key, which component will now act. Control will take care all the things, because here you can see that 3 control we have implemented. One is synchronization and islanding control. Another is current control and voltage control. So this synchronization and idling control will monitor the grid parameters. What are the grid parameters? Grid voltage, load voltage, frequency, theta, grid voltage theta, PCC voltage theta, standalone theta, and all these quantity will be monitored. And once if they are within the limit, because if they are within the limit, then only we can connect this converter with the grid. Otherwise, what will happen? We are not allowed to connect this inverter with the utility grid. So my system will operate in standalone mode. Now, this was all about if we are having only one EV. So how we can connect the multiple EVs? This is the recent research. In this year only, we have published, I think, 4 to 5 papers. Here I have put only 3 in SCI journal only. In SCI journal, International Journal of Energy Storage. This is Q1, I think, or Q2 journal. This is Q3. This is Q2, this is Q1, this is Q2, and this is Q3 journal. So in these 3 journals, we have published this kind of charging station, integration of multiple voltage, multiple EV spot based 3-phase PV array charging station to the modern grid with improved charging capability and power quality. So you can access these papers, you can read And if you are having any doubt, you can mail me if you want to explore this area more. If you want to do the research in this area, I would suggest mostly to the electrical pupils who are doing PhD or masters. They can explore these areas because this is the era of electric vehicles, and the charging infrastructure are playing major roles in the developing of electric vehicles. Everybody is promoting these charging stations. And another SCI journal, we have published renewable energy based charging station with power quality features, multi-V spots, and again one new control we have implemented in this. Here, what we have observed, when the large load is there at the DC bus, this voltage drop down. So for this, to maintain this voltage, PI is having slower response. Proportional integral control is having slower response. So in third paper, we have launched one scheme like robust immune feedback adaptation as well as this optimization approach, so that this voltage can be maintained, or we can find out the parameters of controller in such a way so that it can automatically optimized. Whenever it see like large load is there from the EV side, voltage is keeping down, so it can maintain that voltage and quickly the sag and swell in the DC volt drop or overshoot, undershoot in the DC bus voltage quickly removed. So to maintain this particular DC voltage is very important when we are going to charge these all the vehicles. So here you can see multi-spot based. So we are having AC bus where we can connect the onboard chargers or some kind of AC loads. Grid is there. This DC to AC inverter is there, converter is there. And at the DC bus, you can see that we are having one battery bank, which is at the charging station, 240 volt. One vehicle is also having a 240 volt, another vehicle is also having 120 volt, another vehicle is having 72 volt, another vehicle is having 48 volt. So at the same time, we are going to integrate all the vehicle to the grid, all the vehicle to the grid. And here you can find it out. If the voltage difference is not much, we can have bidirectional non-isolated converters. But once we want to integrate 72 volt with 700 volts, so what we require some kind of isolated converter. And you might have heard the name like DAP converter, dual active bridge converter, where both the side we have power electronics converter and in between, and both the converters are integrated through the transformer, isolated transformer. And this is not a fundamental frequency transformer, this is the high frequency transformer. But high frequency transformer is also having some disadvantage, but they can boost the voltage from 72 volt, or from they can step down the voltage from 700 to 72 volt, because both the times all the time we require charging and discharging. So sometimes we have to boost from we have to buck the voltage from 700 to 72 volt when we require to charge. And sometimes suppose 72 volt vehicle is we want to connect at the AC bus, so we require to boost the voltage from 72 volt to 7. So normal boost converter or normal bidirectional converter will not work at that moment, or this converter have this bidirectional converter, non-isolated converter will have significant losses, or sometimes you may damage the switches also. So it is not recommended to have this voltage ratio gain or high gain converters required in that case. Okay, so this is the design for this two-stage based micro integrated charging station, how the component will be designed, various component, not only one component, because in this case we are having various components starting from PV array. We are having these components, and let me again share my slides. So we are having very to design properly, like this DC bus capacitor also, as well as this this PV array properly must be designed. Suppose we want to design for kilowatts. So how many number of modules, series modules, parallel modules we have to decide. What would be the voltage of battery if you are taking bidirectional converter? What would be the battery voltage if you are taking this DAP converter? So all these things we have to take care. So all the parameters we have designed. Also the voltage IGBTs. I mean, here we have used some control. So what would be the control algorithm involved in this particular converters? So EV battery control is required. VSC control is also required. So voltage VSC control is nothing but current control as well as voltage control. And other side, we require these mode shifting control also, current control to voltage control and voltage control to current control. The boost converter control is also required. So here simple MPPT will be used to extract the maximum power as we are using a two-stage system. And this is the charging station control and grid connected mode. So this is the grid connected control and this is the standalone control. And these STS signal which I have shown you here, these STS signal will decide if they are getting 1. So grid will be connected. If they are getting 0, grid will be disconnected from the system. So here we have utilized these few components, like we have sensed few component using the sensor and PV feed forward. In introduction I have also explained what are the parameters which we have taking from the PV array, and we are deriving one active PV feed forward component which is subtracted from the load component. And EV battery is also, so as I told you, 20 to 80%, 20 to 90%, whatever the limit is there, we can take this SOC limit also in the control so that we are able to discharge and charge the battery according to the SOC of the battery. And we can generate the reference grid current. These reference grid current are compared with the sensed grid current to generate the switching signal for the VSC, this VSC, to generate this VSC. And then other side, we are having this islanded control. So load voltages have been sensed, and these load voltages are converted into DQ quantities. And these DQ quantities after comparing given to PI control to regulate these voltages, and finally we will generate VSC current, and these reference VSC currents are compared with the sensed VSC current to generate the switching signal for the voltage source converter in islanded mode. And this is the how reference voltages will be generated depending on the load theta and source theta or grid theta, we can say. So if this grid outage is there, this will not work, and simple control, fundamental frequency control will be operated like this. If grid is 1, so this error will be given, and this system will be operated in grid connected mode. This is the bidirectional converter control, where so this is having 2 PI control. One is voltage controller and current control. They are nothing but PI control. So this outer voltage control is responsible to maintain the DC link voltage, and inner PI controller, current control, is responsible to maintain this reference battery current. Okay, this actual current to actual battery current to reference current. And after taking 10 kilohertz switching frequency, we have generated PWM signal for this 2 switches. So here 2 switches are connected in this case, in this fashion, in this fashion. Means boost converter and buck converter, like bidirectional converter, buck boost converter. So these 2 switches are getting signal from this particular control. S1 and S2 are going to control the signal, and then battery is connected here. Okay, so this way we can get, so DC bus is connected here. However, battery is from inductor, the battery is connected here. So this way VDC is regulated, charging and discharging of current of the battery is also regulated and operated in either buck mode and boost mode. When we will want to charge the battery, so this converter will operate in buck mode. Whenever we want to just discharge the battery, this converter will operate in boost mode. And then synchronization control, how the voltage and frequency are maintained toward the grid side. So if all 3 quantities, theta error, VT, terminal voltage, frequency, like IEEE 1547, they said that these quantities, voltage, frequency, as well as difference is theta must be maintained within the limit. If they are within the limit, then we can connect to the grid. If they are not within the limit, we cannot connect with the grid. So all the things will be taken care by this control. And PLL has having some disadvantage because mostly used synchronization technique is PLL based. People are using PLL based synchronization technique. Okay, but PLL is having certain disadvantages. What are the disadvantages? These disadvantages have been verified experimentally. So we have used one advanced PLL that is known as enhanced phase lock loop. Enhanced phase lock loop. So what is the disadvantage here? You can say when there is outage or recovery of the grid, the oscillating frequency or the frequency of PLL is oscillating in nature, oscillatory for few cycles, then it settled down. However, if you see the frequency of proposed control like enhanced phase lock control, the frequency is not going to be changed. If you see the signal theta which has been generated using from PLL and EPLL, so load theta and this grid theta, the difference between load theta and grid theta is more in case of PLL. However, difference between proposed technique is very less. So error is more in case of PLL. So chattering error here you can see during the I mean how much chattering error is there in case of PLL. Okay, so variation in angle which has been estimated through PLL as well as from the proposed control. Here, this is the flow chart for energy management in smart charging stations. We are starting from monitoring of grid parameters. So if these PG power coming from the grid is 0, STS are activated and they will isolate because grid is not there. PG is not coming or we are not going to supply any power to the grid. So this STS will be activated and they will shift the system to standalone mode. However, if this PG is there, PG is not 0, then system will be or charging station will be operated in grid interactive mode and we can share the power among EV load as well as utility grid. Certain we have to after that we have to apply one condition like is PV power is more than PV loads and SOC of the battery. If yes, we can see the SOC limit of the battery like the battery which is at the charging station, it is fully charged and SOC of the limit is hitting to the higher limit. Then if yes, then we can feed extra power to the grid. If not, we can charge the SOC till SOC max. Other side, if no, then what we will do? We will check the SOC again, and if SOC is hitting to the higher limit, then we can discharge the battery at the charging station, and we can charge the vehicles. If no, we can feed the load from the utility grid. Onboard charger, all these things will be shifted to the grid. However, other side in standalone mode, again we will check the PV power, we will check these SOCs. If SOC is less than the SOC minimum, then what we will do, we will operate in load shedding. Here you can see if SOC is not greater than SOC minimum, then what we will do, we have to provide the load shedding. We don't have, because PV area is not there, load is not there, then what you will, this grid is not there, then what you will do? And SOC of the battery is also hitting to the lower limit. So we don't have any kind of sources within the charging station. So we cannot supply the power to the onboard charger or load which is connected with the charging station. So we need to do the load shedding. Only emergency load we can switch on and rest of the load can be shut down. And if SOC is greater than SOC limit, yes, we can feed the power to the till SOC minimum. So simulated performance for two-stage three-phase charging station. Here you can first simulation you can see like the performance of charging station when there is outage of grid. So in this case, If outage of grid is there at 0.4 second, you can realize grid voltage is not there, grid current is not there. However, this converter is operating in a standalone mode, and the battery SOC you can realize battery voltage and current. Earlier, it was in floating mode, so we have considered grid connected mode. The SOC of the battery was maintained. However, after standalone, we need to charge the battery, so the battery current is negative here. However, power quality, all those things we have maintained during grid connection. Here you can see non-linear load current. Load current is non-linear. However, grid current is maintained sinusoidal when we have put higher load as well as other things. Here DC link is also maintained, and then the PV array voltage, then the various duty cycles for the boost as well as buck boost converter. And here synchronization, when the grid recovers, at that moment again the battery is shifted from charging. Here we were charging the battery as minus 10 ampere, so after it is shifting to this to the floating mode. Floating modes, neither the battery is going, means the battery is not charging and discharging, it is in floating mode, not operating range. And the DC bus voltage is maintained. Again, the parameters, various parameter from the PV array side, and these duty ratio as well as these what we can say, the other parameters belongs to PV array and these converters, buck boost converter, and these results. And then we are having also results when we are doing load unbalancing, because we have to check the charging station performance and when the load is unbalanced, as I told you. And harmonics here, we are maintaining 4.50 TSD, and this TSD is maintained within the IEEE 519 standard. However, the TSD of the grid is 20, TSD of the load, nonlinear load, is when we are having on board as well as these nonlinear power based load. So 26%, which has been reduced directly to 4.5, less than 5%. And these are the performances of various signals during outage of PV array. PV is there till 0.4 second, but after this point, after 0.4, the PV array is not there. PV array is not there. So what would be the performance? The grid current phase has been changed. So till this point, you can see that we were feeding the power to the grid, as both the voltages and currents are out of phase, because PV power battery was not required to charge. And after this 0.4, PV array is not there, but battery current is maintained. Battery is not required to charge and discharge. Here you can see. So load will draw the power from the utility grid. So the phase has been changed, and now you can see that after 0.4 second, the grid voltages and grid current both are in phase. They are drawing the unity power factor thing. And this experimental results, so a prototype also developed, and we have used a D-space controller, a METEC based solar inverter, as well as these batteries with a 21 ampere hour capacity. As we have restriction from the laboratory side, we are using this 20 ampere hour battery, and semicon based converter we are utilizing. So this is the charging station or system which we have developed in the laboratory. So this is the EV battery with the various voltage 120 and 240 volt we have selected, and then we have a METEC based solar inverter we have taken here, then STS, static transfer switches, various semicron based converters, and then we are having diode as well as these as in non-linear loads, interfacing inductor, all those things we have connected to this side. So experimental results from the from this PV array side, we have recorded the various MPPT performance under various insulation like 1000 watt per meter square and 500 watt per meter square. So here under 1000 watt per meter square, we are tracking the MPPT, as well as in 500 watt per meter square, the MPPT has been tracked very well. And the various results, experimental result under outage of grid, under recovery of grid, when this STS is switching from 0 to 1, so grid is recovered, grid voltage is recovered. Grid current is also recovered. So both are out of phase here, grid voltage and grid current. So excess power is available from the PV array which has been fed to the grid. And these TSDs also here you can see from the PAL Niger we have recorded both the TSD when we have not switched on the converter. You can see the voltage and current waveform. Both are non-sinusoidal. However, once the converter VSC voltage source converter is switched on, both the TSDs from the grid side is reduced from 11% to 3% in the grid voltage, and in the load current we have reduced the TSD from 22 to grid current from 22 to 3.99, that is 4% almost. And 1.9 kilowatt power has been fed to the grid. Negative sign shows that the power is being fed to the grid. Okay, and various performance under outage of and recovery of utility grid. Then we have also these vehicle to grid operation achieved, like from PV array is charging, more power is fed to the grid, and however this load power is undisturbed. So from the vehicle to grid operation and grid to vehicle operation we have achieved. So another topology like operation of this second topology, and we have having various 48 volt converters. So objective of the work like vehicle to grid, other PV source to home, PV source to vehicles, and this is operated in three basic equations are there where KV apply by applying KVL and KCL, and these equations we have achieved. For this equation this operation will be possible, for this equation these operations will be possible. So again one controller we have utilized, and here extra control is like DAP control, dual active bridge control. We have sent the battery current, and we have some constant quantity we have taken, and this particular, because this we are having two converters, converter 1 and converter 2. So switching of these converter must be different when we want to get vehicle to grid and grid to vehicle operations. So these grid to vehicle, during the grid to vehicle, S1 to S8 signals will be applied, and when we want vehicle to grid, then S7 to S2, means in this fashion we have to provide the signal to our these DAP converter, dual active bridge converter. And various voltages we have recorded here, various battery current and battery voltage like 1, 2, 3, 4, and they are having different voltages also. Like here battery voltage is between 100 to 80, second battery voltage is between 100 to 200, then third battery voltage is here we can see, fourth battery voltage we can see like 240 to 250 volt, and fifth battery voltage is around 400 volts. So various vehicles we have realized, and we have funded out operation for multi voltage spot based vehicles, and we have justified our experiment. So we are in the process here in the Manit Bhopal. So the earlier only one vehicles we have developed the prototype at IIT Delhi during my PhDs and all those work. But after that, this work we are, I mean, on this particular topology, we are working on it, and prototype is in process here at NIT Bhopal. We got this one project from SCRB, and we are in the process of developing the prototype. We have procured all the equipments, PV array battery and different battery voltages, different battery ratings like 60 volt, 120 volt, 240 volts. And we have also purchased the microlab box, T-Space microlab box, and we are developing this particular prototype. However, we have verified this topology in real-time simulator also, Opal RT. Okay, at Manit Bhopal, NIT Bhopal. So in similar fashion at the simulation, we have different battery voltages, vehicle battery voltages, and we have verified all the operation vehicle to grid and grid to vehicles out of phase when this solar PV is not there and the grid is drawing power, and again the battery is drawing power. So in this case, the phase will also, grid side phase will also changed. And various intermediate signals of the control, because each time we are using new control, we have to see the operation of this control also. So we have verified these things. And again, the power quality issues we have also addressed. So 4.1 for this three-phase charging station, we have found it out like TSD is 4.1%. However, the load current TSD we have found it out like 21.8%. So here the concluding remark for this particular talk, a charging station have been developed with the various operation, multi-EV spot, single EV spot, as well as we are going to have the vehicle, it will operate in vehicle to home, vehicle to grid, grid to vehicles, various, and we are also addressing the power quality issues. We have to maintain the power quality issues. We cannot say we are putting the large vehicle load on the grid and we are disturbing the voltage and current toward the grid side. That is not recommended. Otherwise, these grid people will put the penalty on these charging stations. So we have to take care these power quality standard also when we are drawing power or when we are injecting or selling power to the grid users. Various control we have shown here, and this PV feed forward loop also incorporated with the current control so that we can improve the charging capability as well as we can improve the dynamic response of these systems. So it has been provided these various choices for the customer to select the charger according to the requirement of electric vehicles. You can select 48, 72, whatever the requirement. If we want to buy the three-wheeler rickshaw, we are having sufficient time to charge during the night. However, if you are buying four-wheeler, we have to run for longer, like for 250, 300 kilometers. So we must have the facilities of charging station. These are the few references which you could follow, and if you are having any doubt, you can discuss right now, or if you are having I mean you want to discuss anything related to further, like how we will go for the research in this area, you can write me mail. If not, I'm not replying initially or in first time, then you keep on sending mails. Definitely I'll try to reply your mails. So that's it from my side, and we can take some queries at the time we are having enough time there. I think this talk was from 10 to 12. Okay, so we can take some queries. If there is any query from the participant, they can ask me. They can unmute me, they can unmute yourself and they can ask the questions. Yeah, that's it from my side.
Thank you very much, sir.
Thank you, sir. Thank you so much.
You explained nicely the design features and way to power considerations related to the electrical vehicles, battery management system, and particularly PV-based charging stations. We got good information along with three-phase charging station with multiple EV spots and hardware implementation related systems for solar PV-based grid. And some of the participants, they have put some queries.
Yeah, please.
How to estimate lifespan of electric batteries, sir?
For estimating the battery, there are other controls also, like SOC estimation is very important, as well as we have to charge the battery efficiently. Suppose I want to estimate the life of the battery and I want to improve the battery life. So my battery is suppose going for a 3 to 4 year. I want to extend the life of the battery from 3 to 4 year from 3 to 4 year to 5 years. So what is the requirement? We need not to send any kind of ripple to the battery. So this by mitigating these ripples, that's why I told you do two kind of control. One is without battery without control and battery with control. So when you will use these controls, so ripple in the battery current will be reduced. Still till now there is no any standard how much ripple we can inject to the battery, but if you are injecting less ripple to the battery, the life of the battery will be improved. Okay, and depending on the SOC, people are having various techniques, SOC estimation technique, by which we can estimate the life of the battery by using these Kalman filtering or other techniques. I hope I have given the answer for this particular question. Let me check the chat box. I'm having.
I'm checking, sir. I'm checking.
Yeah.
Related to the same issue.
Yeah.
How
What is the
how to find position of the battery? That is, if some
to find how to
that
find
is
out the position of the battery?
position means how more time we can use it. Suppose if a battery span is for
Yeah, so
40
depending on
kilometers, sir.
again SOC and DOD, depth of discharge and state of charge. There are two components by which we can find it out, like how many charges are there and for how much time we can utilize this battery. I'm having enough charge and it could be charged like so simply if we see the ampere hour, so 10 ampere, if a battery is having 10 ampere hour rating and it is fully charged, so what do we mean by we can draw 10 ampere current for 1 hour, simple. Okay, and but there are so ideally it is possible, but practically it is not possible because various components, C factor is also affecting the battery life, as well as if like one battery is 6 month old and one battery is new. So obviously the SOC as well as DOD of this new battery will be good as compared to old battery one. So if we have the both the battery rating is 10 ampere, then sometimes you might have you can realize like old battery we are getting only 9 ampere or 8 ampere from 10 ampere battery. However, from new battery you can draw 9 ampere for 1 hour or 9.5 ampere. Means ideally it is possible, but practically it is not possible because sometimes of losses as well as these leakage current, all those things will be involved in these converters as well as in inductance. Also, the various components are connected along with the battery. Not only battery is there when we are going to talk about these depth charger or some other isolated and non-isolated chargers.
Sir, say on the same one, we are getting more queries. Is SOC is dependent on type of battery or not?
Type of battery, yes. I mean, if you are taking like state of charge for this lithium-ion battery, okay, and if you are taking type of this what we can say other lead acid battery, so energy density will depend on like energy density of this lithium-ion battery is good as compared to lead acid battery. So SOC is playing major role. Yes, it is depend on this particular battery, but energy density is also important factor. That's why in vehicles people are preferring lithium ion battery instead of this this what we can say lead acid battery, because energy density of lead acid battery is very poor. So SOC as well as DOD will be poor as compared to the lithium ion battery. If we put two batteries in this and compare these batteries, so you will find out like what is the SOC for lithium ion as well as what is the SOC for this lead acid battery. So the obviously the characteristic energy density, discharging and charging cycles of lithium ion will be good as compared to the lead acid battery.
Sir, how effective related to EVs in hilly areas,
Mm-hmm.
hill
Yeah,
stations?
so yes, so obviously, I mean, when we are talking about hilly areas, so sometimes we are many times, not sometimes, we are getting the ramp kind of roads, or we can say way. So in ramp roads, what it suggested, like people have also realized, like we should require a technology by which we can charge the battery from the brakes. Many times when we are coming down from the hilly areas, so if you are putting the brakes, we can charge the battery, we can restore the energy. This kind of technology is there in the vehicles that would be very effective, because once you are going from down to up, lots of energy will be required. to exhaust this battery. And obviously the battery will be exhausted in this particular way when we are having RAM kind of load. If you are running your EV in the normal field areas and you are running your EV in the hilly areas when we have to go from down to up. So in that case, the energy of the battery will be discharged quickly, because many times you require more power in that roads, RAM kind of road. So if you are providing the vehicle with the by which we can operate, or by putting we can charge the battery, that would be very effective in case of hilly areas. So this kind of technology we must explore, and we can launch when we are going the EVs, or when we are going to use EVs in hilly areas.
Thank you, sir. Next one.
Yeah. Yeah.
Can fuzzy controller can be used in energy management of charging station?
Yeah, sure. People are using various controls for energy management, as well as Kalman filtering. People are using SOC estimations. So it could be used, no issue. Fuzzy as well as neural network based technique people are using for estimating the energy of this particular battery.
Next query, sir. Mr. S.S. Kulkarni is putting the query. Elaborate features of dual active bridge over boost converter.
Yeah. Dual active bridge converter.
Dual active bridge over boost converter.
Boost converter. Okay. So boost converter is non-isolated converter. I would say I will compare this bidirectional converter, which can operate in buck as well as in boost mode. Okay. So in boost converter, we are having this inductor, switch, and diode. More number of component we have to use in case of dual active bridge converter, but when you will go for the high gain, or when the voltage ratio between input and output is more, like we want to boost the voltage from 700 from 72 volt to 700. In that case, the duty ratio will be very high, and the losses in the boost converter or bidirectional converter will be more. So we cannot, and it is not allowable. If you want to keep low losses in boost converter, only 20% duty ratio we can keep, means 20% voltage we can boost from the boost converter. If you are boosting more than 20%, you will find it out like very high losses are occurring in this boost converter. Suppose I'm using a 5 kilowatt converter, and 1 kilowatt losses are there in the converter itself. I'm using a 5 kilowatt system. So 4 kilowatt you will get only if you are putting a duty ratio more than 20%. So it is not allowable. However, if you are putting DAP converter, more devices you have to use, but you can transfer power efficiently. Okay, you can estimate from, or you can boost this 72 from 700, as well as you can buck from 72 volt to from 700 to 72 volt. Because when you are required to charge the battery of 200 ampere hour, you can think we cannot put these isolated converter also. Because the range of non-isolated converter, because the range of these currents as well as very high, and sometimes these converters, non-isolated converters, cannot operate it at that particular current range as well as voltage. So what we have to do, we have to utilize isolated converter for that voltage ratio, and we require very high gain.
Next query from Mr. Sushil. Why still we are using H2SO4 batteries?
Sorry, can you repeat it again?
Why still we are using H2SO4 batteries?
Yeah, sulfur oxide based battery people are also exploring. I'm not a chemical people, so I don't have much idea about the chemistry of the battery. But yes, people are also exploring this S2SO4 battery as one of the reason is energy density is playing major role. So two aspect for the battery technology. One is it can take maximum amount of current. What do you mean by maximum amount of current? Means for fast charging of electric vehicles, we require the battery capacity which can take care or which can take very high current. As we are talking about ultra capacitor, but ultra capacitor having very less charging and discharging time, but they cannot store the energy for a longer period. So if they are not able, but we can have impulsive charging in ultra capacitor. Impulsive charging. In 1 minute we can charge the ultra capacitor fully, and in 1 minute we can discharge. But they cannot store the charge for a longer period. That's why battery technology is still in picture. But if you talk about S2SO4, I think I'm not sure, but I think energy density is more as compared to lead acid. That's why people are another battery technologies are also there. I think another battery are also chemical people are working on it, because the weaker point or weaker link in the electric vehicle is battery technology only. If you are somehow, because after 3 to 5 years you have to replace the most expensive candidate in the electric vehicle is battery technology or battery bank. So if you are somehow, if you are able to increase the energy density, which can be utilized for longer period, and the lifespan of the battery, if you are able to improve, then these electric vehicles will be more effective as compared to combustion engine or these fossil based electric vehicles. So yes, S2SO4 is having higher energy density as well as good charging and discharging characteristic as compared to these two batteries.
Thank you, sir. Next
Yeah.
query is from Dr. Charu Kamesha.
Yeah.
What is cost while charging at home and at charging station?
So obviously the charging at home will be lesser. Charges means the cost at the home will be less as compared to the charge which you will put on the station, because you can charge your vehicle station at a station very quickly. However, at home, if the battery capacity is quite higher, as I told you, I have explained also in my slide, if I'm having a 12 kilowatt battery and I want to charge at home, so how much time it will take? From socket I can draw maximum 3 kilowatt hour in 1 day, in 1 hour. So how much hours it will take? 3 into 4. 4 hours at least it will take to charge 12 kilowatt battery, 12 kilowatt hour battery. Now, if I'm having a charging station which is rated at 50 kilowatt hour, and they can supply 10 kilowatt at a time, so you can charge, or 20 kilowatt at a time, so you can charge your battery, 12 kilowatt battery, within a half an hour or within a 15 minutes if it is rated to 15 kilowatt. But yes, your battery should be acceptable, or your battery should accept that higher amount of current. If it is acceptable, your battery is ready to take that amount of current, it can be charged in 15 minutes also. So accordingly, the cost will be put on you, because you are drawing higher current from the within a half hour, then but the current in the single phase socket is rated, and it is continuously drawn for a 5 to 6 hours. So obviously the charges on charging station will be higher, as we have to include the all the components, like the facility which has been provided at the charging station, DC-AC converters, all those things, and the fast charging is also provided, because certain times we have to shut down the loads also, and we have to provide the power through the EVs. So charging at the charging station will be higher, means the cost at the charging station will be higher as compared to.
Thank you, sir. Next query is from Mr. Ashik. How to handle the issues of burning of battery or some explosion while charging the bikes at home?
Yeah, so that
Some
is
issues
very,
came, sir. At
yeah, that
Hyderabad
is a
also
big
some
issue
issues came.
nowadays, because in nowadays we have find it out, like in newspapers they are in Hyderabad, I think one showroom the battery explodes. So again, I would say, like this chemical technology and the battery technology should be improved. Now, other aspect, it should be tested under various temperature conditions. Okay, means the testing should be done very on the very high priority. High priority means we have to test the battery in the various conditions. Uh, so if and we have to check, like people are putting these batteries, but these batteries are not tested in the extreme condition, I would say. So they have to test these battery. Then only, I mean, government should take the initiative. Like we should make the testing unit of the battery, and we have to test these battery. We have to run these batteries for 50 hours or 1 day or 2 day, and we have to continuously monitor the temperature, because temperature rise is one of the aspect. Well, like in India, the temperatures is varying from minus 5 degree to like 50 degree. So when we are testing the battery at minus 5 degree, and same battery if you utilize at 50 degree, obviously the temperature rise issue will be there. So this thing, by considering the atmospheric temperature, by considering the charging temperature, we have to design the battery, and it should be tested. My opinion is it should be tested extremely on the basis of various temperatures. So somewhere we are lacking in the testing of these batteries.
Thank you very much, sir. You have covered safety challenges also related to
Yeah.
battery maintenance in your answer.
Yes. Yes.
Thank you very much, sir, for your patient explanation.
Yeah.
Very informative session, sir.
Thank you so much. Thank you,
Sir.
all the
Yes, sir.
participants,
Yes, sir.
those who have listened me carefully, and they have asked the good queries also. I mean, because nowadays this EV is growing, but we are also having a various issues like explosion of batteries and these power quality issues, burden on the grid. So, I mean, as I told you, but the basic three ideas are there to developing these AV: mechanical design, one of the aspect, drive technology, and third and very important aspect, charging stations for EV. So thank you again. Thank you so much for inviting me. And I have shared the mail ID, and somebody has also asked for sharing the PPT. So I'll share my PPT to the organizer. They will share with you. Thank you. Thank you all. Thank you all of you. Shall I leave, Dr. Sridhar? Or
Thank you very much, sir. Thank you very much for sparing your valuable time.
thank you
And
so much.
you have given good explanation for the queries.
Thank you.
Very informative section, sir. Hope in future also we'll have fruitful interactions with you.
Sure, sure, sure.
Thank you,
Whenever
sir.
you find time, please. Yeah.
Thank you, sir.
Okay. Thank you so much. Bye bye. Thank you all.
Participants, the feedback link has been posted in the chat box. Kindly fill the feedback form using your unique participant ID, which has been sent to you through your emails. Tomorrow we'll be having another session by Mr. T. Rohit from Germany. He will be addressing various issues on the mechanical aspects. If you have any more queries, you can post your questions in the feedback link. We will send those questions to our resource person, and we'll be getting back to you on the same. Thank you, all participants. We will meet again tomorrow morning for the next session. We do not have any session in the afternoon. Please note, we do not have any sessions in the afternoon. Dear participants, the feedback link has been posted in the chat box. Kindly fill the feedback form by using your unique participant ID. The sessions for today has been closed. We will meet again tomorrow at 10 a.m. Thank you very much. The recordings of the sessions will be posted at the end of the fifth day. Kindly note, after successful completion of the FDP, we will post all the videos to your registered email IDs.